Okay. Well, it turns out both Jan and I submitted talks for Realtime KVM, and we coordinated to go through things step by step, so our talks should fit together relatively well and go through the whole stack of Realtime KVM. I'm starting on the ground floor, explaining what Realtime is, why people care about it, and going from hardware up to KVM. And after that, Jan will go through the whole management stack above KVM, explaining the things that are in that part of the stack necessary to make Realtime happen. Let's first go, what is Realtime? When a lot of people think Realtime, they think it is about doing things very, very quickly. And to a certain extent it is true, but only to a certain extent. Realtime is about determinism. And the things that are needed to get to that determinism almost always result in lower throughput. But for certain workloads, that's fine, because determinism and guaranteed latency are really the most important things. Telco switching is an obvious case where if the software is poorly written and packets do not get routed on time or converted on time, then people's voice will break up over the phone, and if it happens too much, people switch to a different phone company. So they really care about always having sound and voice and other communication routed on time. Stock trading is a similar thing, but worse. If there are multiple client requests coming into the same broker, and the requests of one of those clients are not treated according to the rules, then the brokerage or the stock exchange could get $1 million fines from the government, even if the maltreatment of some of those requests was due to a software bug. So they care about really deterministic performance. If you're talking about rockets, of course, or other avionics things, it is even more important. If the computer that controls your rockets goes into a garbage collection cycle and it doesn't do anything for half a second, you could deal with an exploding rocket. Or if you're the military, you could deal with a rocket that doesn't explode on time, which is just as bad. So this is something where people really care about response times happening when they expect a response. And for different workloads, you're going to have different maximum latencies or maximum response times. And some of the cases, for example, telcos, they might be okay with occasionally having a response that takes a little longer, but only very rarely, because they do not want their customers to get upset that their voice breaks up all the time. Go back to the same slide that Paulo showed. Basic rel 7.2 is the red graph, and almost all the time, the normal kernel has low latencies. But almost all the time is not good enough for some workloads. And that is why the real-time kernel exists, just a green line. And nowadays also the real-time KVM setup. That's the blue line. The average latencies on the real-time KVM setup, they are almost certainly going to be higher than the average latencies on even a non-real-time kernel on bare metal. But again, it's the maximum latency that is really important, because every single request that comes in needs to be handled within a certain deadline. As usual, the biggest pitfalls on a system are the BIOS, the firmware, and the BIOS. On x86 systems in particular, system management mode and system management interrupts, they're always good for trouble. System management mode is used by hardware vendors to implement certain hardware features in software. For example, if I were to press the brightness increase or decrease on my laptop here, chances are that it's not going directly to some microcontroller that controls the monitor. It will actually trap into the CPU. And the CPU it receives the system management interrupt, and it will switch to system management mode. It will stop execution of all the tasks on all the CPUs in the system. And it is not going to return control to the operating system until the monitor brightness has been adjusted. And it's used for all kinds of things in system management. It might be used to control fan speed on a server. It might be used for that nice management console that you connect to over the network. And this runs completely outside the control of the operating system. In some cases, it can take milliseconds to run. And really, if your hardware prevents your operating system from running for several milliseconds, there is no way you can guarantee microsecond latencies. You're just going to be unable to meet your deadlines if your hardware does not let you run. So this is an issue that really has to be fixed at the hardware level. For many servers, it is possible to disable some or all of these features in the BIOS, just by going into the BIOS configuration and disabling thermal management, disabling power management, maybe disabling hyper-threading. There are all kinds of things that can have an influence here. On the other hand, there are also some systems that are not fixable here. I'm not looking at anybody in particular. If I'm looking in general direction and you feel guilty, please fix your hardware. But the lesson here is that if you want to run real-time, you need to buy hardware that can actually do real-time. And there are some tools to help test whether or not your hardware is capable. There is a hardware latency detect module that basically runs at a very high real-time priority in the kernel, and it disables the interrupts on that CPU, and you just leave it running there overnight or over the weekend, and if it notices any large latency spikes, it will log them. And it can also check the SMI count in the CPU's MSRs and see whether such latencies were because of an SMI that happened. Linux, of course, has latency issues that are similar to what is found in the BIOS, but for different reasons. In a normal Linux kernel, we have critical sections that cannot be preempted. We cannot schedule anything else while we are in an interrupt, while we're holding a spin lock, or even while we are holding the RCU read lock. We cannot reschedule that CPU until the lock has been released or the interrupt code is done. That means that if we have a really high priority program that wants to run, but currently we are running some low priority program that is holding a kernel spin lock, the high priority program is going to have to wait. This leads to unacceptable latencies, and in real time, kernel developers have been working on this for many years to improve the situation. A lot of the real-time preemption code has already made it into the mainline Linux kernel. Some of the patches for the config preempt RT stuff are still in a separate tree, which Stephen Rostad maintains, and Thomas Gleixner and other people. And they actually have a talk about how to get that code upstream at Plumbers today, I think at 11 o'clock. And there are several URLs where you can find more information on real-time Linux. Well, in order to not run into the issues of spin locks and IRQs and things like that, a lot of things have to change. Some of the features that are necessary you may already be using without knowing it. For example, a deterministic real-time scheduler that always schedules the highest priority programs across the whole system, across all the CPUs. That's already upstream. Kernel preemption is already upstream. Priority inheritance mutexes, you're probably not using them, but they're there. The high resolution timer is something that is very useful for real time because it allows people to set a timer for any point in time, and the CPU will fire the timer and wake up your program whenever you want at essentially an arbitrary timer granularity. This has been upstream for years, and everybody uses it for all kinds of things. But it's one of those things that was developed for real-time originally. Preemptive read copy updates, spin lock annotation, no hertz full mode, things like that are all upstream. A few people are using it. But full real-time preemption still has a number of things left that really need some significant work to get upstream. The goal of the last pieces of the real-time preemption code are to make every part of the Linux kernel either preemptible or of very, very short duration. And this is necessary in order for the highest priority task on a CPU to preempt everything else. Not just lower priority tasks, but also kernel code that is holding a spin lock or interrupt code. How do you do that? Let's take a look. The preempt RT code, it turns spin locks into priority inherited mutexes, which means that for every lock in the system, not only can the task that is running the lock go to sleep and wake up again later, we also keep track of who wants the lock and who currently has the lock. It greatly increases the overhead of these locks, which makes throughput of everything lower. But it allows us to always interrupt, preempt whatever program is running. There's a little bit of code left running with raw spin locks, but not much at all. We do priority inheritance. I'll get to that again in the next slide. And threads are used to run interrupts. It seems not that big a deal, but it means that if you have an interrupt on the system that is less important than your real-time program, you can stop running the interrupt code for a little bit, and then you can go back to running the program that you want to run. And interrupts can also be given priorities, just like any other program that's running on the system. The read copy updates, lockless synchronization, it does not track CPUs in a real-time preempt kernel, but it tracks tasks instead. And it does not allow the system to move on to a new RCU grace period until all the tasks that were using RCU or that had an RCU read lock in an old grace period have moved on. And with so many more things to track than just the CPUs, of course the overhead there also increases significantly. Well, real-time is pretty hard. Turns out that real-time with KVM is even harder. and we had quite a bit of fun trying to make that work. One of the issues that Realtime preempt nicely solves is always running the highest priority program on the system. However, the host has no idea which of the guests is running the highest priority program. It's not visible to the host. The only thing we can really do is mark all of the vCPU threads with real-time priority, and we just have to treat them all as the highest priority thing in the system, with maybe the exception of ksoft_qd, so we can deliver interrupts to vCPUs. Kernel housekeeping tasks that might introduce 1 microsecond of latency on a bare metal real-time kernel, those might introduce 3 or 4 microseconds of latency on KVM. The reason for that is that it is possible that both the host and the guest kernel want to do this housekeeping thing at the same time. For example, a timer tick. Not only that, but handling one of these things from a guest may require multiple exits from the guests into the host, switching back into the guest, doing something else that goes back out into the host. So where on the host you might deal with one operation, having the same operation happen on both the host and the guest simultaneously, you might look at half a dozen different things that all need to happen. So there were certain things that did not pose any major issues to the bare metal real-time people, where we had to make kernel changes in order for them to not be prohibitively latency introducing for us. Another thing that we cannot do is priority inheritance, because the host kernel cannot see which tasks are running inside the guest, or what locks they might be holding inside the guest. And inside the vCPU, we have similar issues where the task that is running may not be preemptible. There were a number of changes that we had to make to the kernel in order to make real-time KVM work. There was something in the no-hertz code that marked the CPU as being quiescent for RCU, which means the CPU would not get poked to run callbacks or to move on to other grace periods when running user space code. That code was not yet active when running in guest mode, so we added that. There's a parameter to disable syncing of the KVM clock with NTP changes on the host. If you have a larger guest, it can take a significant amount of time, where a significant amount of time is a few microseconds, to adjust the KVM clock data on all the vCPUs. If we disable that, the guest will no longer get NTP corrections. You may have to run NTP inside the guest if this is something you care about. But it does remove a source of latency. If you're running a real-time task and there is another task runnable on the CPU, the no-hertz full code did not disable the timer tick. It would only disable the timer tick if there was just one program running. But if we never want to run that other program because it's really low priority, then we should disable the scheduler tick anyway, because having that on both the host and the guest introduces too much latency. We have a parameter to make the timer for a guest fire a little earlier, to take the wake-up latency of a guest into account. And there's various little enhancements to the ISIL CPU's code and the work queue code, just to move more of the kernel housekeeping tasks away from the real-time CPUs and to the system CPUs. Priority inversion and priority inheritance is another issue that we cannot do in a virtualized environment, because the host does not know what locks are being held by tasks in different vCPUs. And a vCPU thread running a very high priority program, it may need to take a lock that is held by a vCPU running a much lower priority program. But if the host does not know that, there's just nothing we can do to help one program release a lock that a higher priority program needs. And the vCPUs always have the same priority. We have no idea whether a vCPU is running something important, or even if the vCPU is idle, if we're running with idle poll. And that means if you're looking at a particular physical CPU on the host that has a vCPU thread on it, having a higher priority thing on the host on that same CPU is usually unacceptable, because it will interfere with the latency of our vCPUs. But having a lower priority thing on the host, on the same physical CPU as a vCPU, could lead to a system deadlock, because something that the system needs to have done on that CPU might never run. The vCPU thread could take 100% of the time, and it might take days or months before something really low priority on that CPU ever gets run. So we really cannot share a CPU that has a real-time vCPU with anything else running on that same CPU. We have to separate out the parts of the system that run real-time things and that run something else. It looks something like this, where in this case the system has been split into 3 partitions. We have system tasks that run everything else, and we have 2 real-time guests, which each get half of the real-time CPUs in the system. And everything else that is not real-time does not get to run on the real-time CPUs. Those all run with the system tasks. Seems like a good solution, but it's not enough. We need to also do partitioning inside the guest. Because inside the guest, we may run into a program that writes to the emulated graphics card. At that point, QEMU will trap not just to the host, but in the host kernel we will see, oh, we have a program that is trying to do something that is not emulated in the kernel. We have to run the QEMU emulator thread. So we go all the way from the guest into the host into QEMU. Inside QEMU, we may have to wait for something else to finish doing whatever it was doing and release a lock. And they can take a really long time. At that point, if you have a program with very low priority that is not real time, trying to write to the graphics card inside a guest, at that point, that guest vCPU is not running. It's waiting for the host, and it is waiting for QEMU to do something. And we are unable to switch from that low priority program to a higher priority program until QEMU is done. So the guest also needs to be partitioned. And it looks very similar to what we did for the host. We boot the guest with ISO CPUs. the real-time tasks run on the real-time CPUs, and nothing else runs on those CPUs. Everything else is running on the system vCPUs. And this way, things that might trap to QEMU, or that might do something that needs emulation in the host, or that does anything else that takes a really long time, it will not preempt the guest, or it will not prevent the guest from switching to a real-time task on the CPUs where we want to run a real-time task. Dedicated resources are something that we can probably get away with today. Because you can buy CPU that has 18 cores. You can buy a system that has multiple of those CPUs on one board. So it's relatively affordable to buy a system that has dozens of CPU cores. And real-time applications are relatively specialist. So it is something where the people who really want to guarantee that their programs always respond within, say, 50 microseconds, that they're willing to throw a little bit of money at the problem and buy systems that just have CPUs dedicated to running real-time tasks. The numbers that we found in the latest tests by Luis are actually a little better than I have on my slides. I think in 24-hour tests, he is now down to a maximum latency of 13 microseconds. And this is with a test called cyclic test with a stress tool running in the background. This is a slide that I took from Kernel, and OpenOffice somehow did not do the text on the x-axis correct after I moved it over. So the middle graph everywhere is the bare metal real-time kernel on RHEL 7.2. The slide on the left has the maximum latencies in there. And we actually have to remove the maximum latency from the graph to see how bare metal RHEL 7 and real-time RHEL 7 compare to KVM. You can see that the average and minimum latencies on KVM are significantly higher than on bare metal. Almost a factor 3. But virtualization has some advantages for certain people, so they're willing to live with a slightly higher latency. And what really matters for most real-time customers is that the maximum latency is really low, and we guarantee that with the real-time KVM stuff. So, there are many, many things that you can do to break real-time. And for every single one of them, the advice boils down to, don't do that. Real-time is not a thing that you can magically achieve with better software. You need a lot of software changes to make real-time happen, but you also need to set up your system in a very careful way. And the system configuration has to be just right for real-time to work. Things like CPU frequency changes, and hot plug, loading and unloading kernel modules, moving a task, a real-time task, from an isolated CPU to a non-isolated CPU or the other way around, changing your clock source, running a system with real-time tasks that does not have enough memory to keep your real-time tasks from swapping. Basic things like that. They all ruin your real-time performance. And you want to be really careful when configuring a system to do real-time. You want to make sure that your devices are always fast enough to do everything that you want to do. You want to make sure that you have enough CPU available to handle all your requests. If it takes, on average, 20 microseconds to handle a request, and you might get 10 requests simultaneously, and your deadline is 50 microseconds, you're going to need several CPUs to handle them, because one CPU would take 200 microseconds to process those 10 requests. And simply by not having adequate resources available, you might not be able to handle a large enough number of requests. So real-time systems always have to be oversized. If too many requests come in at a time, you will not meet your deadline. So you have to know what your workload looks like. You have to know, I can get at most 5 requests in at a time. And my deadline is maybe twice the average. So I need to have at least 3 or 4 CPUs available to guarantee that I always make my deadline when I have a large number of requests coming in at the same time. Intel has some new technology out there in new CPUs to help with this. If we have a system out there that has a single chip with 12 or 18 or 30, who knows how many CPU cores out there. Currently, it is possible that one CPU core is running some program that causes the data that all the other programs have to be evicted from the CPU cache. This can break real-time response times because there really is only so much stuff you can access in RAM in a few microseconds. You can access a number of things because DRAM latencies are still pretty low. They're on the order of 60 nanoseconds. But if you were to access a few hundred different things from DRAM, you might no longer be able to make your deadline. It's just easy to add up all those latencies to something exceeding 20 or 30 or 50 even nanoseconds, whatever your deadline is. So we're at the point now where low latency real-time actually depends on data being in the CPU cache. If your data is not in the CPU cache, you might be unable to meet your deadline. But with cache allocation technology, you can set quotas for different programs, and the CPU will make sure that programs do not have too much data in the level 3 CPU cache. And that in turn makes sure that the other programs do not have all of their data evicted from the cache just because somebody is running a program that streams through a few hundred gigabytes of memory looking for something. And this really helps improve the guarantee of low latencies on systems where you have many CPU cores on a single chip. One of the major conclusions of this talk is real-time KVM is actually possible. This surprises me as much as it might surprise some of you. But we managed to get it to work. But it is largely achieved through system partitioning. An overcommit, like you would do in many other virtualization situations, is simply not an option for real-time. For real-time, you want guarantees. You want to make sure you can always do what you have to do on time. So your system has to be larger, and you cannot use all the resources. But within these constraints, we can actually get really low latencies. And, well, real-time applications need to be written carefully, because if your real-time application does something that is really slow, it's not going to be a fast program. And this includes all kinds of syscalls that may be slow. This is no different from bare metal real-time. Virtualization, I think, has a place in real-time because it really helps with system isolation, which can help customers do things like deploy a real-time virtual machine today, and when they upgrade their hardware in 5 years, they could continue rolling out the same real-time guest with the same operating system and the same virtual hardware running on top of new physical hardware. And this way they can take advantages of improvements in hardware without having to requalify the whole software stack. And, well, it takes a lot of very careful configuration, which Jan's presentation will go more into, because I don't really have the time to go through the entire stack. We've got a few minutes for questions if you have any. Oh, and you can ask your questions at one of the microphones in the middle of the room.
Hi. So Rik, you used ISO CPUs, to have partitions. The other way is use, that has some disadvantage, right? Because it's static and you need to reboot to change the partition. The other way is to use a C group CPU set. You can do that at runtime. And actually we played with this, compared ISO CPU versus CPU set, C group CPU set. Okay. The only difference we found so far was the HR time, high resolution time. And my question is, do you still see advantage of ISO CPU, or do you think we can use a C groups CPU set?
In the long run, I hope we can use CPU sets in C groups. But right now, there are a certain number of things in the kernel that are removed from ISO CPUs. But if you use CPU sets, they still run. And that includes things like unbound work queues and other housekeeping tasks in the kernel. And right now, ISO CPUs is the only thing that removes those things from the real-time CPUs. I would like to change that in the long run, but it's just not something that we have gotten around to.
Okay. One workaround we found was just an offline process of then online. Do you think it works or not?
That's a good question.
Okay. Okay. Okay, thank you.
Hey, Rik, so you know what? I just have a few questions, or actually a few comments. So the first one is that one of the biggest problems we have is driving enough timers into the kernel. So like for LTE applications, especially within the core, you have to drive like 500, 600, 800 timers into the kernel. And so when you do that, you get about 20% CPU overhead. And, just wondering if you guys have been focusing on that. And then the second issue is, as far as partitioning, so we need data plane partitioning, control plane partitioning, and also timeshare partitioning within the guest.
Yeah, I think for the things that we focus on, we're not really sure at this point what workloads people are going to use this for. And I think the things that we end up focusing on next will change when people actually start running applications on this. We will no doubt discover new bottlenecks besides the various system things that we have discovered that we have moved out of the way. And partitioning-wise, you have little choice but to make sure that nothing gets in the way of your real-time task. But inside the guest, it may be possible to squeeze things a little more. If you have lower priority and higher priority programs, and you know some of the lower priority programs are never going to run anything that traps to QEMU in the host, then it may be possible to be a little less strict with the partitioning inside the guest. I don't know if that's what you're looking for.
Yeah, I guess, what I noticed is that if you run cyclic test, it'll give you, so inside you get kind of pretty good, latencies and stuff like that. But then on the host, you get like 20% overhead.
Yeah, there is.
And I think, that might be due to the timer injection or something like that. Could be the timer code injection doing that.
Well, yeah, there is significant overhead to running real-time. And having it both in the host and the guests, it definitely adds up. But that's something where I think in the long run, we can work on improving some of those things by making some of the code that are real hot paths, lockless, for example. We can get rid of some of the locking overhead that the real-time code introduces currently. But that's really a longer-term project because we really want to get it to work first.
All right, thanks.
Hi. Just one quick question regarding the lock priority inheritance. You said you're not able to get in the hypervisor the information which real-time characteristics the special thread had. Do you think there is some way of para-virtualizing this?
That's a good question. In theory, it would be possible to para-virtualize priority inheritance by telling the host of the relative priorities of everything going on inside each guest. But I think in practice, that might introduce so much overhead that we would no longer meet the low latency real-time deadlines.
Okay, thanks.
Okay, one last question, and then I'll hand it over to Jan.
With regard to CPU isolation, do you have any guidance on how many CPUs are needed for the host and the guest to effectively do their work? How many can we take away from each of them to run
I think
real-time applications?
On a minimum, you will want to have one CPU core per socket for system tasks on the host. But it also depends on what you are running, the specifics of your workload. And if there are many things going on the host, you might need more.
And in the guest?
In the guest, it also depends on what you're running. 1 or 2 CPUs might be enough. But it's again very workload specific, unfortunately. We're right on time. I'll hand it over to Jan Kiske.